So far today we've seen criteria for the similarity of triangles. We saw, what was it, 4 different similarity criteria. And they all relied to some extent or another on a constellation of theorems that we talked about first. 3.2.1, which, so we see these figures showing up a lot, figures that look like this, where 3.2.1 guarantees for us that if my two sides, DE and BC, are parallel, then I get a proportionality, not between the sides of triangles, but between the lengths of the line segments that we see in this figure, AD to DB and AE to EC, stand in the same proportion. So it's not quite a statement about similar triangles, but it can be used to prove the statement about similar triangles that we find in 3.2.4, which generalizes the midline theorem, to say that as long as DE is cutting my triangle in such a way that it's parallel to BC, so if I can take that parallelism for granted, that was a consequence in the midline theorem, but which we don't have in general if we're not bisecting the sides. But if we can take that parallelism for granted, then that gives me the similarity between the triangle ADE on the one hand, so the smaller triangle in this figure, and the triangle ABC, which is the bigger triangle in this figure. And crucially, there's also a converse to lemma of 3.2.1, which we later on call by the name of lemma 3.3.6. But I don't believe that we need the intervening material in order to prove 3.3.6. 3.3.6 just says that this is in fact an if and only if statement. So I could erase the word if from here. DE is parallel to BC if and only if the ratios of these line segments are the same, one to another. So this actually goes both ways, and we end up using it in both ways when we go to prove these similarity criteria. So the first of the similarity criteria that we saw was AAA, that for a triangle, congruence of angles is sufficient for equiproportionality of the sides. To prove that, we, as we very often do, take two triangles whose corresponding angles are congruent, so they satisfy the AAA criteria, and we just situate one of them inside the other. So we get this figure over here on the right. And from there, we just need to justify how it is that we know that B prime C prime is parallel to EF, because after all, if we can guarantee that those two sides are parallel, then 3.2.4, the generalized midline theorem, will give us the similarity of those two triangles. And all we needed to do in order to guarantee that those sides were parallel is to reach back into our bag of tricks from 1.3, this theorem about parallel lines and alternating and adjacent interior angles, that says that because by construction this angle and this angle are congruent, and this angle and this angle are congruent, I think we only really needed one of those pairs, treating DE as a transversal to the, treating DE as a transversal to the lines of B prime, C prime, and EF. 1.3.1 will guarantee for us, because of the equality of those angles, that those two sides are parallel. And because those two sides are parallel, 3.2.4 gets us the rest of the way home, to guarantee why the smaller triangle in this figure is similar to the big triangle in this figure. And then, and this is an argument that we end up making more than once, we just need to justify why that means our original triangle is also similar to the bigger triangle on the right. And we do that by just observing that by construction, it's congruent to this smaller triangle that we see over here. And because congruent triangles are in particular also similar, right, just similar with a proportionality constant of 1, all we really needed to know was that ABC was similar to A prime, B prime, C prime. And then, because similarity of triangles is an equivalence relation, we can read from left to right to guarantee that ABC is similar to DEF. And so that was the tricky part of the proof. It was going the if direction. That two triangles are similar if all three corresponding angles are congruent. The other direction is manifest just from the definition of similarity. the only if direction. Two triangles are similar only if all three corresponding angles are congruent. In other words, if I have a pair of similar triangles, then the corresponding angles are congruent. Well, that's part of the definition of similarity, because the definition of similarity requires both congruent angles and equiproportional sides. So if we have both of those conditions, then in particular we have each one. And so we have congruent angles guaranteed if I have two similar triangles. So a lot of these proofs end up, if I were studying these to try and remember these proofs, you won't have to because you'll have a resource on the exam, but I think I would end up getting turned around because a lot of the arguments are very similar. We saw in the intermediate step here that even though having all congruent angles is enough for similar triangles, it's not enough for other similar figures. In particular, as soon as we go to quadrilaterals, we can come up with an example of two quadrilaterals whose angles are all correspondingly congruent, but which are not in fact similar. Just take a square and then stretch that square out by a factor of 2 in one direction, and we get two rectangles that are not similar to one another despite the fact that all their angles are congruent. For here we move on to the more difficult similarity criteria that begin to bring in some equiproportional sides. So SAS, where the A is capital and the S's are small, is the statement that if I have two pairs of equiproportional sides and they're joined by a congruent angle in the middle, that's enough to give us similarity between that pair of triangles. And again, we do it by situating our known information as kind of a subset of one another. So we begin with the length AB and the length AC, and I'll draw these in here, the length AB, the length AC, and the angle in between them. And then we use that same angle and a pair of sides that stand in the equal proportions to the sides that we drew before, and we just make the argument that if we embed the latter figure inside the former, where the angles are congruent, which is why we know that we can embed it exactly inside the former. That from there we end up again using 3.3.6 to argue for us why the side DE in this figure and the side BC in this figure are parallel. Because as soon as we get parallelism of those two sides, that's enough to give us the similarity of the smaller triangle here to the big triangle in this figure. And once I have that, because I constructed the smaller triangle as a congruent copy of our PQR in this example, that was enough to give us similarity. And so the stroke of ingenuity in this proof is how to go from the proportionality of AD to AB. So how to go from our original comparison, which is a comparison of a part to a whole, right, of the lengths of sides on this side of the triangle, to the kind of comparison that will allow us to use lemma 3.3.6, which is a comparison of one part to the other part. Right? That's the difference between the flavors in those theorems. So we started with the yellow comparison, but what we wanted was this orange comparison. And the algebra that makes that run is taking our proportions that we know and subtracting 1 from both sides of that equation in a clever fashion. So on the right-hand side of the equation, we subtract 1 as the fraction AC over AC. On the left-hand side, we subtract 1 in the form of AB over AB. We do that, first of all, so that we have common denominators to subtract. But then the great part is, when we do that subtraction, the numerators turn us from a whole minus a part into the other part that makes up that whole. So AD minus AB gives us DB because AD and B are collinear. They belong to the same side. And likewise, AE minus AC gives us EC, again because those 3 points are collinear. And it's that comparison of one part to another part that plugs us into lemma 3.3.6, that guarantees for us the parallelism that we need to plug in 3.2.4 and give us the similarity of those two triangles. So again, similar argument, but we needed a little bit of ingenuity to go from a part-whole comparison to a part-part comparison that lets us use lemma 3.3.6. And our final similarity criteria are SSS, in which case we look at all of the equiproportionality of the sides and deduce the congruency of the angles. And then finally, AA similarity, where we claim that we only need 2 congruent angles to give us similarity. So starting with AA, the engine behind this observation is just the fact that in a triangle, if we know 2 of the angles, we automatically are dictated the third by Theorem 133, because the interior angles of a triangle have to sum to 180 degrees, no matter what. So 2 triangles cannot have a pair of congruent angles unless they have all 3 angles congruent. And if all 3 angles are congruent, then the AAA similarity criterion applies. So AA similarity is a fairly short trip away from AAA similarity. All we need is that the sum of the angles in a triangle adds up to 180. So the last really elaborate similarity proof we had today was SSS, which this, I think, to me, was the least intuitive of the proofs that our author lays out, where what we really need to prove is, again, the direction going from right to left. That if we have equiproportional sides in a pair of triangles, then we also have congruent angles, and so we have similarity. So that's the side that's interesting, because the forward direction is obvious, again, from the definition of what it means to be similar. So there's nothing to prove going forward, but there is something to prove going backward. And this proof relied on the construction of points G and H, which simultaneously satisfy 2 conditions, that GH is parallel to BC. That parallelism is something we worked hard to prove in our other proofs that we looked at today. Here we're kind of assuming that it works, that we take it for granted. And we do it in such a way that GH and EF are congruent segments. So this side and that side are congruent to one another. If we can take for granted that this is possible, if we know that we can do that, then the snowball pretty quickly gets rolling with our parallel line theorems again, that give us the congruency of the alternate angles, the corresponding angles, with treating AB as a transversal to the parallel lines BC and GH. We get congruency of those angles and congruency of these angles. And because then I have 2 angles that are congruent, I also have 3 angles that are congruent, again, by the same argument as we ran over on the right-hand side of the screen, and that gives me the similarity of the triangles that we were looking for. And then the only remaining step that's not immediately obvious is that just because the smaller triangle on the left, AGH, is similar to the bigger triangle on the left, ABC, what does that mean about our original triangle? Because at this point, we really only have 1 pair of sides in that pair of triangles that are congruent. We only have GH and EF as congruent sides. And so the last part of it is we use the equiproportionality of ABC's sides to DEF's sides, so we use the information in the blue box, connected with the similarity of those 2 triangles to connect the ratios that we get out of the similarity with the ratios that we got out of our assumption of equiproportionality that will guarantee for us that not only is the horizontal side of this pair of triangles congruent to one another, but the other 2 sides are as well, giving us congruent triangles by SSS. That's what 1.2.3 ends up being. So in a way, this proof was about going from lowercase s's, which is our similarity criterion, to discovering a way to bring in capital S's, our congruency criterion, instead.